So this lecture is designed to just be hitting the high points on MANOVA, but MANOVA is the multiple analysis of variance, where you're able to compare the means of groups with multiple outcome variables. So multiple analysis of variance is once again going to be used when we have more than one dependent variable and it is inappropriate to perform a series of univariate tests. So similar to with ANOVA, where it was inappropriate to use a bunch of t-tests, now we're looking at it from the perspective of wanting to combine a bunch of ANOVA analyses and trying to reduce the experiment-wise error in that. So MANOVA is once again an extension of our ANOVA that is used when we have two or more dependent variables. So the MANOVA procedure makes inferences to identify if we have different levels of independent variables having a significant effect on the linear combination of each of the dependent variables, if we have interactions between independent variables and the linear combinations of the dependent variables, and if there are significant univariate effects for each of the dependent variables separately. So MANOVA works well in situations where there are moderate correlations between dependent variables. But if we have high or low correlations among our dependent variables, it's not really going to be a very good idea. So for example, if they're too correlated, we don't have enough variance left over for the after the first dependent variable is fit. And if the dependent variables are completely uncorrelated, we're going to lack power in our multivariate tests. So what might our research questions look like in a one-way MANOVA? So we can test the overall null hypothesis. Can we reject the null hypothesis that the vector of means on all outcome variables is equal across all groups? So like I said before, with our earlier example in ANOVA, if I'm looking at third grade classes from all subjects, we're assuming that they're all equal. So it wouldn't matter who your teacher is or how long your teacher's been teaching. All of our math scores across the 10 different third grade classes are going to be statistically the same, as with all of our English scores, science scores, and social studies scores. So that would be one research question that you could use for a MANOVA. Another one would be, can you detect the differences in previous omnibus tests? We might want to do a follow-up analysis. So let's say we run it and we see that there does seem to be a difference. Well, now I might want to get into a more detailed test and I might want to take it a step farther. So now I might want to say, let me look at all science by itself, or maybe a way of assigning years of experience or some sort of ranking. So it might be, depending on how it turns out, that I've been wanting to actually go into some further analysis. So in terms of notation, we want to use the bold mu in our hypothesis equation to indicate that this is talking about a vector matrix. So remember, when we run our ANOVAs separately, they can't take into account the pattern of covariation among our dependent measures. And so it's possible that if you run a bunch of ANOVAs, you're not going to get some of the nuances that will get picked up by a MANOVA. And so you could be running several ANOVAs and it would show that there are no statistically significant differences. But when you run that MANOVA, you do see that difference. MANOVA is sensitive to not only our mean differences, but also in the direction and size of our correlations among our dependent variables. And so when we're working with a MANOVA, we're asking, is there a significant difference among our groups based on multiple response variables? So really, it's just looking at ANOVA with two or more response variables. We will calculate the centroid of a group. You'll build a probability distribution around that centroid for the purposes of comparison. And then you can run repeated t-tests. Just make sure that you use adjusted p-values for the multiple comparisons so that you can compare the new data to the groups. But MANOVA does this all at once. And so some assumptions of ANOVA, just like with any other type of ANOVA, are univariate ANOVA, we're going to assume that the scores on our y outcome variables are quantitative and approximately normally distributed. For the others, we're going to use similar assumptions that are used with what we call the general linear model. And with those types of analyses, we're going to assume that all pairs of y variables are linearly related. Ideally, they should have a multivariate normal distribution, but sometimes that's difficult to assess. So in practice, we end up looking at the univariate and bivariate data screening to help evaluate the assumptions of our normal distributions and linearity of relationships between our pairs of y variables. And so we can do this by looking at our box plots, right? So we look at the box plots for our response variables, and we look at the shape of the distributions, and then also kind of where the box plot whiskers end up. Another thing that we need to look at are our residual plots. So when we're testing for normality and equality of variance, if we have a normal distribution with equal number of points along our observed axes, we have equal variances spread out on either side of the mean, predicted value being 0, we're good to go. But if we have non-normal distribution, which would be an unequal number of points along our observed axis, with our equal variances spread on either side of the mean being 0, we might want to perform some optional fixes. If it's normal or non-normal, we need to look at our histogram or do a normality test. If we have unequal variances like a cone shape, either going away from or to 0, these have to be fixed for us to do an ANOVA, and so you'll fix that using some transformations. And then if you have outliers, those are points that deviate from the majority of the data points. This has to be fixed for MANOVA because MANOVA is highly sensitive to outliers. So if you violate any of the assumptions of MANOVA, you need to transform your data, or you might want to choose some non-parametric options such as PERNOVA, which we're not going to discuss in this class. So remember with looking at ANOVA, when we partitioned our variance, we partitioned our variance with sum of squares between with sum of squares within to get our sum of squares total, right? And so you can take these two values, add them up to get your total variance or sum of squares for everything in your data set. With MANOVA, we're looking at the sum of cross products total. But basically, we're just looking at the output of these matrices, and the sum of the cross products between plus the sum of cross products within is still going to equal our sum of cross products total. So it's essentially the same thing. It's just we're now looking at, instead of single variables, we're looking at sets of variables. So we can go through these matrices, and we've got the omnibus test statistic. So here we're going to be working with Wilks lambda, which when we use Wilks lambda, we want that value to be small when we're looking to determine whether or not our MANOVA is statistically significant. As MANOVA designs become more complex, we get more complex matrices. So the more and more variables that we're going to have in our model, the more complex it gets. The nice thing is we don't have to do it by hand. You can throw it all into a statistical software package, and it does all that calculation for us. You can use SPSS, some other tool. I think you can do it with Excel sometimes by expanding your ANOVA, but Excel's really good for ANOVA, but you can't really use it for MANOVA. So you need a little bit more of a robust statistical package tool to do this. We have effect size. Effect size is very important. So we know that the larger my sample and our population is, everything will become statistically significant. So really, this is all about understanding at some level that depending on how big my sample and or our population is, how that's going to impact my analysis. So if I have a sample size of 1 million, pretty much everything is going to turn out statistically significant. So you really have to get inside of that, and so it's important to understand effect size because that's certainly going to influence the interpretation of my results. So if you look at other types of analysis, you can take your this Wilks lambda, and in the statistical package, it's going to get converted to an F value. So generally speaking, when we're looking at an F value, we want to see a big value because then I am more confident of the statistical significance of my model when my F value is big. MANOVA does not include the eigenvalue lambdas associated with each function for each effect in the MANOVA in some outputs, but they are still an omnibus test statistic for your MANOVA analysis. So the first three multivariate statistics that we have here for our test statistics combine information across a set of eigenvalues for all the corresponding discriminant functions. However, they combine the information in different ways. So when there is an underlying variate, will the four test statistics necessarily be the same? So it's going to be important to know which test statistic is best in terms of test power and robustness. So when you have a small and moderate sample size, the four statistics will differ little in terms of power. If the group differences are concentrated on the first variate, as well as often will be the case in social science research, Roy's statistics should prove most powerful because it takes into account only that first variate. And then the next one you might want to look at is Hotelling's trace, then Wilks lambda, and Pillai's trace. So, but when the groups are different among more than one variant, the power ordering is going to be reversed. So, in that case, Pillai's trace would be most powerful, then Roy's root is least. So our final issue pertinent to the test power is that of our sample size and the number of dependent variables. It's going to be recommended that using fewer than 10 dependent variables unless you have a really big sample size. In terms of robustness, all four test statistics are relatively robust to violations of multivariate normality. Roy's root is not robust when the homogeneity of covariance matrix assumption is invalid. When sample sizes are equal, Pillai's trace is the most robust to violations of our assumptions. But when sample sizes are unequal, the statistic is affected by violations of the assumption of equal covariance matrices. So as a rule, with unequal group sizes, you're going to check the assumption of homogeneity of covariance matrices using Box's test. And if this test is non-significant, and if the assumption of multivariate normality is tenable, which allows us to assume that Box's test is accurate, then we can assume that our Pillai's trace value is accurate as well. So Wilks lambda uses this notation here with the capital pi, which indicates that the terms are multiplied as opposed to adding them. Wilks lambda indicates that across all the two main functions, the proportion of error or error within group of variance is high, and looking at the proportion of error or within group variances. Pillai's trace takes eigenvalue divided by 1 plus eigenvalue and corresponds to the ratio of sum of squares between divided by sum of squares total. A high value in Pillai's trace indicates that across all the different functions, the proportion of variance in scores due to in between groups variance is relatively high. So again, we're talking about a relatively high variance value. Hotelling's trace, here we see this capital T that looks like it's italicized, and so we're looking at this sum of eigenvalues again. So we're looking at the ratio of the sum of squares between divided by the sum of squares within. A large value for Hotelling's trace indicates that the ratio between groups to within groups is high across all discriminant functions. So again, here we're looking at the ratios of variance across your discriminant functions. Roy's largest root is eigenvalues divided by 1 plus the eigenvalue, and it's looking at the ratio of sum of the squares between divided by the sum of squares total. Roy's largest rate uses only value of 1 for the first discriminant function. So Roy's largest root corresponds to the squared canonical correlation for the first discriminant function. So instead of looking at all of them, Roy looks at the first function. And so that's probably the biggest difference among your four different analyses to look at for your variance among your variables. So what does the null hypothesis for MANOVA look like? We've got this bold mu symbol, and that's how we know it's MANOVA as opposed to ANOVA, is that we've bolded our mu. Remember, many statistical packages are going to convert each of the multivariate statistics just described to an F values. And so depending on the situation, this may be an exact F value, it might be an approximate F value. But if F is judged to be statistically significant, then we can reject the null hypothesis. All three sets of tests will include all the discriminant functions. So remember, if my test is statistically significant, I reject the null hypothesis. This is independent of the techniques that you're using. So that is how we reject the null when we have statistical significance. So some preferences, I think we mentioned this before, but Pillai's criterion or Wilks lambda are going to be preferred when our basic design considerations are met, such as sample size, violations of assumptions, approximate cell sizes, equal cell sizes. Pillai's criterion is considered more robust and should be used if our sample size is smaller, if we have unequal cell sizes, or we have issues with homogeneity of covariance. Roy's GCR is a very powerful test statistic if the researcher is confident that we have met all of the assumptions. And the dependent measures are representative of a single dimension of our effects. So in most of the situations, all of the statistical measures will provide similar conclusions. So let's go through an example real quickly. We have high school seniors that have indicated what type of degree, field they want to follow, so business, medicine, or teaching. And we have aptitude tests in reading, English, mechanical reasoning, abstract reasoning, math, and office skills. And so the first thing you would see after maybe some summary statistics is your multivariate test. And so here, if we're looking at Pillai's trace, we see that we have a value of 0.987 with a really large F score for all of these. So that tells me that it's statistically significant. Our Wilks lambda is statistically significant, and we want that to be small, so with our Wilks lambda, that's 0.13, so that's going to be a good value. Next, we see the Hotelling's trace and our Roy's largest root are the same value. And if you go back to the slide where we look at those formulas, it's the eigenvalue divided by 1 plus the eigenvalue. So it's not really surprising that we get the same value for these two tests. Let's see, if we look at the values for career group, the first one is the intercept for your career group. And again, we have Pillai's trace of 0.317. And now we have the individual F values for each of the different analysis techniques to determine our statistical significance. And so this is kind of chopped up version of the MANOVA chart. And so if you notice the output for the MANOVA, you're now looking at all the different response variables for one independent variable, in which case here we were looking at career group selected by the student. And so this is going to be, the same format that you see for your ANOVA table, where you've got your sum of squares and your degrees of freedom, then your mean squares, then your F statistic, and then your significance for your F statistic. But we have quite a few more variables than what we've looked at before. So looking at this output, the main thing that I see here is that our math scores and the office scores are going to be significant for both our model and our career groups. So here, if we look math and office, we have significant values here, and then we also see it up here in our corrected model. So here we're looking at the output for the Tukey HSD, or honestly significantly different test. And so now it's looking at all of our independent variables and comparing them against each other. So we've looked at English and used that as the value that we're assessing business with medicine and teaching social. So medicine and business and teaching are the things that we're looking at. And so it's looking at each of those differences between the scores across our variables. And so if we look at this mean difference column, we still see the ones that are indicated with a star, the ones that are the statistically significant difference. And notice that those are all the ones between business and medicine and teach social and business, and then business and teach social, and then medicine and business, and then medicine and, teach social and business, and then business and medicine, right? So we see here that business is clearly different from our teaching and our medicine groups. Um, and we see basically that in mathematics, their score is lower, and in our office skills, our score for business students is higher. And so here we are looking at the output from the two key post-hoc tests. If we look at the English scores based on English, up here we have 27 observations in the medicine group, 28 in the business group. 98 in the business group, and 39 in my teaching group. And so all this is looking for is the homogeneity of these groups. And we can get all this for all of our variables, as you can see here. And so this is, just one of what we call a post hoc test that's available for the MANOVA analysis.